Hi, good afternoon, everybody. Thank you for attending our webinar today. My name is Jody Schollard with Chicago White Metal Casting, and today we're going to be talking about design for manufacturing and how that relates to cost savings related to the die casting process. Again, thank you very much for attending. I've been with Chicago White Metal just over 8 years in the die casting industry for about three years longer than that. And I'm the Southeast Sales Manager for Chicago White Metal, so some of you may have seen me around or might in the future if you're a new prospect, new customer to Chicago White Metal. The panelists today, just a note of housekeeping, everybody's phone is currently muted, but there is a way to ask questions, and we'll get to that here in a second. We have a couple of panelists on the line, John Miller and Mike Dimitrov. They will be answering your questions as we go through the presentation today. And how do we ask questions? If you look at the right part of your menu board for the webinar, you'll see a section of questions. And if you just type in what question you have, hit send, Mike or John will be answering those throughout the presentation. It might take us a little bit of time to get through all the questions depending on how many come in. So please bear with us, but we will get to your question as we go through. A little history on the webinars that Chicago White Metal has presented over the years. This is our 7th in the last, I think, 3 years that we've been doing webinars, and they have a very wide-ranging topics for the die casting process. We started with product solutions through die casting, which was sort of a die casting 101 introduction to die casting. We looked at surface finishes for die casting, which was a very popular topic that we covered. We looked at conversion opportunities, such as machining, changing from machining to die casting. We looked at the miniature zinc die casting process as a whole separate webinar that we performed. We looked at various ways to save cost on die casting. Some of those, again, are covered today, but that was a specific one just on 10 ways to save on die casting. And then the most recent webinar that we did was on magnesium die casting and the various advantages, disadvantages, and various topics on magnesium. Again, today's webinar is designed for manufacturing. All of the webinars that we've done in the past, including the one today, have been recorded and will be placed on our website for future viewing. So you will get a link once the webinar is finished today that tells you how to log on and find the past webinars, and if you want to listen to this one again today, you can do so. So what's the agenda for today? We're going to look at the design for manufacturing process cycle, and this relates somewhat to how Chicago White Metal does it, although it's probably fairly common to other die casters, but we do take a look at how CWM does this process and would like to do this process on a new project. The first thing to look at is we review the application for the new project, the details, the requirements, go through pretty detailed analysis of how the part's going to be physically used in its application. It obviously will help us be better informed and help you make decisions on the best things to do with your die casting. We then take those requirements and we step into the die casting part design. Look at various ways to reduce cost as we go through that, alloy options, do we machine a feature or do we cast a feature, those type of things we look at. And then we take that design and we'll do a mold flow analysis, and that really helps us define the design properly and look for very minute details that might have a big impact on cost, and we see that a lot of times when we do the mold flow and can use those results back into the die casting part design and further improve the part development. And then we'll take, once that's finalized, we look at the detail drawing and we look at notes and tolerances and datum schemes and other type of things that are associated with what you'll put on your drawing. And we help you step through that and try to avoid some things that might add cost or complexity. And then we'll wrap all this up into a case study where we look at one product all the way through development and see how we step through all these items. So application review. Basically, as many details as you can tell the die caster, the better. That would even very small details we have found can have a big impact on the cost and overall performance of your product. We'll ask about mating parts. We'll see if you can give us maybe samples of mating parts. Maybe you've got 3D models or 3D prototypes available that you could provide. Maybe models, 3D models are available that you could show us how our die casting is going to mate with the other components. And you may ask yourself, well, why does that matter? Why does the die caster need to know how the parts go together? Well, we can really help identify any issues that might be there regarding how the part is mated. Are there galvanic corrosion concerns with one type of material mating to another? Are there different parts that we can combine together? If we see our die casting is going to be mated to a stamped part or another machined part, something like that, we may say, hey, we can make a modification in the tooling such that you can make both these parts at the same time, and that would obviously be a big cost savings. And we'll look at how that comes about in our case study that we're going to talk about here shortly. We ask about environment questions. How's the part used? What type of environment is it in? Is it in a marine environment? Is it in high heat environment? And all those type of questions and understanding of how the part is used will help us guide you through alloys and part features and that type of thing that might help with the overall product. Product testing, what type of testing is the die casting and the overall product going to go through? That, again, will help us identify the right type of alloy and part features. And if it's going to be drop test, well, maybe there's a component or a section of the die casting that would be weaker because, and not be able to withstand a drop test versus a change we could do to add a rib or strengthen the part, that type of thing. Is your requirement that the die casting be leak tight? That is a fairly common thing that comes up, and we have additional questions and solutions maybe that will help that factor. For example, might the part need to be impregnated with an epoxy sealer to help seal up any areas that might tend to lead themselves to leak throughing. We look at the cosmetic and finish requirements. Is your part cosmetic? Does it need a powder coat or wet paint, or is it going to be in an environment that requires a tremendous amount of corrosion protection? That's the type of things we'll ask in that section, and will really help us identify the best options for you, and we can step you through that. We have a little mantra here, start with the finish in mind, and that goes back to the webinar we did on surface finish, and it really, knowing how the end product is going to look and the requirements for the finish really will help us in the part design up front to try to help steer the product in the right direction. And the last quick tip, just work with the die caster. It's our recommendation that has the capabilities from start to finish for all these process steps. Chicago White Metal does have those capabilities, so we would obviously be included in that list, but that's our recommendation, is to work with somebody that has them all. It's sometimes difficult. One company will just die cast, and then they'll have to send to another company to machine and another company to coat, and that does tend to add some complexity that might not need to be there. So how do we do that? How do we ask these questions and really work through with the customer to understand the application? We utilize GoToMeetings, which is what we're doing today. Basically, this is GoToWebinar, but or other web-based services to help step that through. It's a great way to get our team and your team on a call, look at 3D models on the screen. We can move things around and see how things interact. We can look at mating parts. So it's a great opportunity to try to get a lot of details up front reviewed and try to optimize it as best as we can. Another option is to host a die casting seminar at your facility. That's something that Chicago White Metal does. I do it a number of times during the year, and it's a fantastic opportunity to have somebody come in, spend an hour. Usually it's about an hour over lunchtime. Most of the times companies will have a lunch and learn session that they can utilize their lunchtime to have a company come in and give an overview of the process and what their company does. And it's a great way. It can be tailored specifically to your needs. And if you want to talk more about surface finishes, or you want to talk more about miniature zinc process, we can really tailor it to what you're looking for. I bring a number of samples with me so you can see what other people are doing in the industry and how how their die castings are designed and different features for different industries, and it leads to a number of brainstorming ideas. Another option, which I know sometimes is a little more hard to do, is to send a team to the die caster. Come to Chicago White Metal, review what we can do, see our capabilities, take a tour, see the processes, see what's the latest going on in the die casting industry. And it really helps develop a process or a partnership with a die caster to come in and meet with us and see what our capabilities are. You know, you might 2 months later down the road, you may say, "Wow, I wish we knew somebody that could assemble a component onto this die casting." And, oh yeah, Chicago White Metal does that. They've got great assembly capabilities. So let's talk to them about what they might be able to do to help. Okay, so now we know application. We reviewed what's going to happen with the die casting. So how does that transfer or translate into part design? So what we would recommend is to start with the NADCA standards. NADCA stands for North America Die Casting Association, and is a great resource with a number of publications and technical information, and it's a great starting point when you're doing a design, especially from a tolerancing standpoint and surface finish and what to expect, and it's a great starting point. Then that leads into alloy selection. Chicago White Metal has and other resources are available to show all the different alloys that are available for die casting, what the material and physical properties are of each, and it'll help you identify with your die caster what alloy is right for your application. Wall thickness is very, very important, and we'll talk about this in a case study, but one of the first things we do when we take a look at a new part that a customer might send to us is we take a look at wall thicknesses and say, okay, is there areas that are too thin, there's areas that are too thick, and that's a big thing we look at, and that goes back into which alloy is being selected, because each alloy does have its own limits and capabilities regarding wall thickness, so that's another factor. We looked at cast versus machined features. Are there features called out that are supposed to be a machine that we might be able to cast in? Obviously, the desire is to cast in as many features as possible for cost save and less complex design, but maybe a feature has tolerances that we can't quite hold as a die cast, and will need to be machined as a secondary operation. That's some of the things we look at. Are there other types of things such as tapped holes are going to be required? Well, maybe there's an option to use a self-tapping fastener instead and save cost and assembly steps and that type of thing to save money. Other part design topics we look at are draft and parting line. Obviously, a big thing for die casting. All die castings will have to have some amount of draft in certain areas. We'll take a look at this here coming up. And in the parting line, how is the tool going to be designed, and where's the parting line and gate and overflows and vents going to be placed around your part? And we'll talk with the customer about that and say, hey, this is where we're planning on gating. Does this look okay? Is this going to interfere if there's a little bit of gate vestige left? Is that going to be okay location? Is it going to be visually acceptable because it does have a little rough area where the gate comes in? Is that going to be a cosmetic concern that we might have to deal with? So some other topics that we discussed. I talked about uniform wall thickness, and this is where we talk a little more about that. Every alloy is going to have a different wall thickness limit. So get with your die caster, talk about what the application is going to do, what requirements are, and we'll step you through and see what wall thickness allowances are best for the part and based on what alloy you're choosing. As much as you can be consistent with wall thickness, that's the best. Die castings don't have to be 100% consistent as far as wall thickness throughout the parts. You can have thinner sections and thicker sections, but depending on where they are in the part, you can see some issues with either visual cosmetic concerns with how the part is designed, or potentially even flow issues. So as the metal fills the tool and fills your part, If it goes from a thin section to a thick section, sometimes that's not the best situation. Those type of concerns affect tool life. If we can be consistent throughout the part, tool life is typically longer. It's also faster cycle times. If you can imagine, as the part fills and solidifies, going from a thick section to a thin section back to a thick section can affect how long the part takes to cool and solidify, and your cycle times can be affected. So again, that's another factor. We talked about cosmetics. Sometimes cosmetics are affected by the different wall thicknesses throughout the part. And you can see on the little screen here the blow-up image of two cases. The one on the left is what we would consider a good case. It goes, the thickness is fairly uniform throughout the cross-section here. On the right, the thickness goes from a relatively thick section down to a pretty thin section and then back to a thick section. And that is a potential issue point with the tooling and how the part is going to fill. So that's some of the things we'll look at and discuss with you when we see areas like that if we can address ahead of time prior to the tool design and tool build, that's the right spot to do it. Reducing heavy masses, this goes along with the wall thickness topic we've been talking about. This is another area that we really look at when we get a new product in. We'll see if there's any real thick sections in the part. As you can see, this is a cross section of a theoretical die casting. And as the part fills and solidifies in the tooling, what happens is the outside area of the part, which we call the skin, solidifies first in the tooling. And that is where your really dense, low porosity material is after the part is cast and solidified. The interior section of the casting takes longer to cool and solidify, and that's potentially where you'll see areas that's called shrinkage porosity will form. As the material shrinks and solidifies, you'll have little tiny spaces where porosity will be left. All die castings have porosity. The key is to try to minimize it and minimize where it is in specific parts of the of your component. Here you can see on the right section, this what's calling out as a thick section. This will take much longer to solidify and cool than the other sections of the part will. So you'll have the potential for more shrinkage porosity in that area. So what we do is when we take a look at a new component, we'll ask the customer and see if there's ways to reduce the thick section. Excuse me. So, for example, can we come in with a tool section from the bottom or from the top of this area to core out and remove a good bit of that material to try to get the wall thickness down something closer to what's the rest of the part is. And that's a real big advantage in reducing that amount of porosity, increasing the strength of the part because it'll, in effect, add some ribbing to the part. And it's a great way to improve the overall condition of your part if we can remove that thick section. Another topic with part design is our cost trade-offs. There's always trade-offs depending on what you want to do in the part. And in this slide, we're looking at whether or not it's best to machine a feature in or add a side core in the tooling to core a section out. And you can see on this part, if you can see where my cursor is moving, there's these two risers on the top side of the part that have a hole going through them. And there's two options to make this. Either you cast these risers in as solid pieces and then machine out the hole, or you add side actions in the tooling to core those out. And there's cost trade-offs with those. The part price would be better if you cast those features in. Tool price would be higher if you do that, but depending on the volume of the project, if there's a good bit of volume, then maybe the added tooling expense to cast those features in would be an overall product cost savings. Some things to consider when looking at this: if you add side cores to the part to remove those features or to cast in those holes, There may be parting line areas that are going to be somewhat visually unacceptable or visually unappealing, let me put it that way. And you may have to have those removed depending on where they are and what your cosmetic requirements are. Machining after the fact, after casting, is obviously going to be able to hold tighter tolerances. So maybe those cast holes can't be held as tight as you need them, and we have to come in and machine them, and that's the best way to go. And then the last item is to not forget about porosity, and this goes back to the slide I had a minute ago, which I'll show again. But if you come back in and we cast these risers solid and then come back in and machine them out, potentially what you'll be doing is machining through a thick section which had an increased chance of the shrinkage porosity that we talked about here. So that's a factor to consider, that when you machine through that area, potentially you'll expose some of that porosity, and that might not be acceptable for what you're trying to do. So maybe in the end, casting those features in is a better option, and then maybe if those tolerances are not achievable by casting them, maybe we come in with a touch-up operation to just machine out a small amount of material and not the entire amount. So there are cost trade-offs, there's tolerance trade-offs, so just something else to consider. Continuing on with part design, one other note with the cast versus machine, sometimes the as-cast features or as-cast surfaces provide a more consistent geometry, so that's another something to consider. One of the other things we look at is can one or more mating parts be integrated into the casting? I talked a little bit about this earlier, but here's where we do that. We're looking at part design, and we're looking at how this relates to the other mating parts, and we'll ask is, are there areas for consolidating components together and trying to save you money from the total product standpoint. And again, the case study we'll show here shortly, that is a big factor into that case study. What are the coating requirements? Again, start with the finish in mind. Remember our little catchphrase. Is this a very, very cosmetic part, or is it, or are there performance requirements from a salt fog requirements or other type of requirements that we'll have to get a specific type of coating for? Are there galvanic corrosion concerns? Depending on how this part goes mates to the next part, we'll need to make sure that there's no interaction between those different types of metals that might cause some corrosion issues. And many, many more different the questions that come up during part design. But this will give you a feel for the way we step through when we talk about environment. We talk about how the part is used, and then how that translates into the actual part design. So what's next? So now we've got the part design relatively close to what we think we're going to want. And so what we do next from Chicago White Metal standpoint is we do a mold flow analysis on every new project that comes through our door. It is a fantastic tool that we've used for many, many years to try to finalize that design process and optimize it as best we can. And this also helps us to design our tooling. So it helps us design where the gate should be, where overflows should be, how much cooling to put in certain areas of the part. It optimizes cycle time, so we can try to have the best cycle time that we can do for the customer. We typically do this after tooling kickoff. So once we get a purchase order for a new project, the mold flow analysis is part of the tool design. But an option that we could do and really is an advantage is if we can do it early. The cost for the mold flow analysis is included with our tool price that we provide. But there's a way that we could potentially break out the mold flow analysis portion of the tooling price and do it up front and before the actual project gets kicked off, if possible. And what that does is it really allows us to save an enormous amount of time and money if we can do that up front before everything gets kicked off, because then it helps the overall project timeline and can get that going faster. It's also much easier to do any kind of changes that are going to be required to the part if we're able to do that up front. And we have on here that it's a design loop. So the results from the magma mold flow analysis will go back. we'll take that, we'll see if there's certain areas of the part that might need to be modified just a little bit to improve overall performance. So this is a bit of an iterative process, but it's one that is a tremendous advantage. We've done studies and taken case studies to show that we can really anticipate and recreate issues that we've seen in the past through this mold flow analysis, and so it gives us a tremendous amount of confidence that we can prevent these up front. So here we'll talk about our case study for today. This project was for a very high-end video projection system, and you can see the parts on the right here. This is what the starting point was. So it was a two-piece magnesium assembly. These parts were actually Thixel molded instead of high-pressure die-cast. Originally, that's how they came to us. Both parts required a certain amount of machining on them, which we had to do separately, obviously, since they were separate components. There were a number of seven assembly screws required to put these components together. And there was a lot of stack-up tolerance issues with these parts. When you consider the assembly components and getting these parts together, it really made the overall product tolerancing undesirable from the customer standpoint. And obviously, the more parts you have, the more logistical coordination there are from getting these from supply bases, and in this case, these were from offshore sources. So we worked with our customer to come up with a rough idea of what we wanted to do. We talked with them and decided that the best thing to do would be to take all of those components that you saw on the previous page and make as one. So instead of two die castings, now we've got one large one, which obviously would simplify logistics, save cost in a number of areas. Customer only needed to buy one tool instead of two. The critical machining tolerances, instead of having to do them on individual components, we were able to do them on a single part, which made it a little easier to hold the tighter tolerances. And all those stack-up issues associated with the assembly components were removed. So we knew this was feasible, but there were still some design tweaks and changes that we would have to do to finalize it. So here we looked at the part from a draft standpoint, and as I mentioned, all parts are going to require, all die castings are going to require some amount of draft in certain areas. Depending on the alloy, that makes a difference on how much draft you need. Size of the feature has an impact on how much draft you need. So every case is different, but in this case, we took a look. We decided where draft needed to be, how much in certain areas. As a rule of thumb, typically between 1 and 3 degrees of draft are required for a part. Again, it can be less than that in certain features, but that's a rule of thumb. NADCA provides some guidance on this. And I would just recommend talking with the die caster to go through the part and look at it as a case-by-case study. Radii are another very, very important aspect that we look at with a new part. Die caster is going to ask for as much radii as we can get. Really aids in how the metal flows through the part during casting. It helps prevent tool wear, helps prevent cracks that are associated if there's a very, very sharp corner in the part. That helps alleviate any crack concerns. And again, talk to the die caster, look at the NADCA standards, and really go through the part from a radii standpoint and try to get as good a design as you can. This, again, is where magma mold flow analysis comes in very, very handy, because it highlights areas that might be a concern with respect to radii and draft as well. So now we've got the part looking pretty much like we want it, so it's ready for its mold flow analysis. So here's a picture that shows this is looking straight down from the top of the part, and we identified the bottom surface is where we'll gate into the part. Pretty large side actions actually to make each right side and left side of the part. and then the vending edge on the top. So all the air will be forced out of the opposite side of the part here. This is what the resulting runner looked like. So you can see the biscuit of material here, gate coming in at 4 or 5 different locations on the gating edge. Actually, another gate location here on the right to help support metal into this right side of the part, which is very, very important. And then the rectangular features that you see are the overflows on the part where we try to get all the air and porosity and other things you don't want in the part to end up. Instead of in the part, they end up in the overflows. So here's a quick visual of the mold flow analysis, and this is related to velocity. So there's a number of different characteristics that we look at with mold flow. Velocity is one of them. This is velocity of the metal into the part. And I'll get the animation running here. So you can see how the metal fills, splits off into the various gate locations, and then begins to fill the part. In the end, for velocity and for many of the other images we'll look at from the mold flow analysis, you really want it to be in the light blue shade as much as you can. So here you see that the high velocity areas are concentrated into the overflow outside edge rectangular features that are actually trimmed off and not used on the part. So that's what we want. We want those features to have all the air and the other entrapped gases instead of on your part. This is another analysis that's done with mold flow. This is the air entrapment analysis. And on the left, you can see this was a kind of a before image. And this was the first attempt at the air entrapment analysis that we did. And again, we want everything to be in the real low light green, light blue areas. And for the most part, it did. But you'll see on the left side of the part, you see some red and yellow areas on the left wall here. And then again, on the opposite side of this large round feature, there's some darker blue getting into the light red areas, which we had a concern about. So what we did was we took a look and said, okay, what's going on here is that the metal, as it's entering the part, is having a hard time getting around this large rectangular opening in the middle, and it's also having a hard time getting around this large circular opening on the right. And so when all the metal comes back together, it's got some potential problem areas on the opposite side. So on the right view, we see what we did, what the results were after we added a couple of features. You'll see a rib of material that was placed on inside the rectangular feature to help metal get from one side to the other better. And then again, a rib of material that we added on this right circular feature. And all it is just to help metal get from one side to the other better and help the properties of the part as it fills. And then those features are trimmed out or machined out after the fact, so they're not there any longer once the part is completed. So here were the final results from the case study, and then again, as we talked and discussed, it was a win-win for both the Chicago White Metal and the customer. Two large die castings, or large castings were converted into one single die casting, eliminated the assembly components and assembly process that went along with that. The overall part weight was reduced. Many of the internal features were more simplified versus what the original design was. The machining we talked about, it was easier to do the machining required as a single piece versus the individual components. Oops, here we go. The overall dimensional stability and accuracy was greatly improved with this part as a single piece die casting versus the multiple components. And in the end, the customer saved about 40% on the total component-related cost, which is a great cost-save application. So the last one of the last topics we want to talk about is drawing development. So now we've got, think about our process for design for manufacturing. We talked about application. We talked about how the part is used, how the part goes together in the assembly, how the mating parts are assembled to the casting. We looked at how that transferred into design, part design, talked about how that went through the mold flow analysis, and again, continuing to optimize part design and try to get cost out of the part. So now we've got everything completed, but now we want to look at the drawing and what some of the things that go on the drawing from a note standpoint and tolerancing and data schemes, and just some things to be cautious about and to think about. Datum schemes are obviously very, very important for the customer and for us, and so we'll work with you to figure out the best way to develop those and make sure everybody can measure them effectively. Tolerances are very, very important. We take those very, very seriously and look at it as to make sure that things that are designed to be held as cast can be held as cast. We wouldn't want to add machining operations or secondary operations to hold tolerances if you don't really need them. So we'll work with you and say, okay, hey, this tolerance over here we have a concern about. We may have to add a machining operation. Is there something we can do to increase that so we can hold it as cast and not cause any excess costs to be placed on the part. Note here to be careful not to just carry over notes from past drawings. Many of the projects we work with, the part might have started off life as a machined part, CNC machined from billet, and volumes got high enough where it made sense to change this to a die casting, which is fantastic. We do that a lot, and it's a huge cost save. But sometimes what happens is that the notes that were on the drawing as a machined part just get carried over onto the die cast drawing, and that could be problematic depending on what the notes are. But just a caution to make sure that the notes for die casting are actually applicable for the die casting itself. Are the notes too strict? Are there certain things in here that are they're going to cause excess cost to have to be put in and that type of thing? And we'll look at that with you and see if we can come to an agreement on what the best overall note strategy we can do on the drawing. Is the part leak proof? Sometimes we just get a note on a drawing that says part must be leak proof. Well, that means a lot of different things for a lot of different people. So depending on what the application is and what the requirements are, we may have to add a 100% leak testing process. You never know. So just putting leak proof is not quite enough to get us into the best condition. So we'll work with you to determine if some sort of leak testing or other requirement is needed on that part. Same with porosity. Sometimes the porosity notes that customers put on drawings are overly complex and really do add cost into the product where maybe it isn't needed. So again, just a caution to work with a die caster and come up with a plan that makes sense for everybody. Ejector pin flash and surface finish. Again, those depending on the requirement, sometimes we see notes that are overly strict. And the last item, keep in mind that some of these features might change over time. Again, for ejector pin flash and surface finish, when a tool is brand new, the surface finish will be fantastic, and the ejector pin flash will be virtually zero. But over time, after tens of thousands of shots on a die, you will start to see a little bit of ejector pin flash in certain areas. You will start to see some surface finish things that are a little rougher than what a new tool looked like. So even though a note might have been fine at the beginning of a tool life, halfway through that feature certain features on the tool might not meet that some of these notes anymore, and we'll have to come back to you and say, hey, is this okay still, or are we going to need to add some sort of secondary operation to to clean those up and to make them look better. And depending on the application, it may be fine, but we would want to bring that to your attention and make sure that that we're still meeting the drawing. So it's just another caution to look at, consider that some of these features might change a little bit from when a tool is new to when it ages. So that's the end of our presentation today. We have some additional information that we'll be sending out to you, as well as want to highlight the fact that there's a tremendous amount of information on our website. And so we invite you to visit the Chicago Wet Metal Design Center and look through, and there's guides, and there's white papers, and there's alloy selection guides. There's a tremendous amount of information to find on there, and we invite you to take a look. As I mentioned, this webinar, as well as the previous webinars, were recorded and are on our website. So I invite you to go back and listen to those, and if you missed some of the earlier ones. And then we will be sending out to all the participants a design and specification guide for custom die casting that Chicago White Metal publishes. It's a great kind of introductory to die casting. Gives an overview, a lot of the topics we talked about today, but also some other topics that we did not cover. And there will be a downloadable link to that guide with the email that's coming out following this webinar. Again, I want to thank you very, very much for attending today. If you have any questions at all, feel free to contact myself, anybody else at Chicago Wet Metal, but here's my contact information. And if you're in a different part of the country, not the Southeast, feel free to contact me still, and I will make sure you get in touch with the right people. But we look forward to working with you on a future die-cast project. And again, if you have any questions, please don't hesitate to contact us. Thank you very much.